Welcome to Unit 12 of this course. In this unit, we will be looking at how to model controllers with timing constraints. We started off this course with a goal to come up with reliable controllers, right? So we said that there is code controlling the functioning of many of the devices that we see around us. In particular, controllers need to stick to strict timing constraints. For example, a controller, say for example this automatic gear control, when a request for gear change is made, the response should be within a certain time limit. A controller for a pacemaker should listen to heartbeats and respond if there is no signal within a certain time limit. So clearly, many of the safety critical systems that we see around us have strict timing constraints. And the question of model checking systems with timing constraints is extremely important. We need good solutions to model check systems with timing constraints. This is what we will see in this unit. We will see one way of adding time to transition systems. How do we model controllers where time comes into picture? Let's start with the first example. We had seen this train gate example in a previous unit. Let me recall. So this is a railway crossing and there is a gate which is controlled by a software. We need to make sure that the gate is down whenever the train is in. Let's see a model of this system. So let's start with the train. So the train is initially far. That's denoted by this far state. When it's approaching close to the crossing, it sends a signal approach and comes to the state near. This means that it is near the crossing, and then it sends the signal enter and gets into the crossing. That's when it is in the in state. When it's sufficiently outside the crossing, it will say that it has exit and it will go to the far state again. Okay, far, near, in, again far. What about the controller? So these are some discrete states of the controller. When the controller listens to this approach signal of the train, it will go to some state called 1. Now in this state, it will start lowering the gate. It will send the signal lower to the gate. And then when the controller receives the exit signal from the train, it will raise the gate back. And this is the model of the gate. If it initially it's up, if it receives the signal lower from the controller, it will go down. When it receives the signal raise, it will go up. So this is the usual transition system that we have been seeing so far. The joint behavior is given by this handshake operator, which is some synchronous product. So from far 0 up, when there is an approach, far goes to near and 0 goes to 1. Okay, that's the state change. So based on this idea, this is the transition system of the joint behavior. If you see, there is a way in which the train can be in, but still the gate is up. Okay, this is not a safe state. In this very abstract model where we have not taken care of timing, it is possible that the train is in, but the gate is still up. And this is an unsafe state. So what we will do, we will add some timing information into the model. Let's see how to do it. Firstly, based on the speed of the train and other physical properties, we can make certain assumptions about the time taken for the train between the approach and the enter signal. Okay, assume that once the train sends the approach signal to the gate, it takes at least 2 minutes to actually come into the crossing. Now, what about the controller? Once the controller receives the approach signal, in exactly 1 minute, it will send the lower signal to the gate. And the gate, after receiving the lower signal, takes at most 1 minute to bring it down. Okay, these are the assumptions that we are making on the timing based on other parameters. Now, the question that we are interested in is, suppose you are given these timing information, how do you model it in this transition system? That is the goal of this unit. We will be seeing what are called timed transition systems. So this is the usual one. We wanted to say that between approach and enter, there is at least 2 time units delay. To do that, what we will do, we will add a clock to this model. Now, what is this clock? It's a real valued variable and it's assumed to increase at the rate of global time, in the sense that initially the clock is 0. Forget about these two. Assume that this transition system has a clock. Initially it is 0, and as and when time elapses, the value of the clock also increases at the same rate as time. Now what happens when the train gives the approach signal? The value of this clock is set to 0, and you make sure that this transition is taken only when the value of the clock is bigger than or equal to 2. Let me show this diagram. We wanted to say that between approach and enter, at least 2 time units have to elapse. And for doing that, we used a clock in this model, and we set the clock to 0 when the approach was given, and we say that this transition can be taken only when the value of x is bigger than or equal to 2. So once x becomes 0, in this state the value of x increases as and when time increases, and once 2 time units have elapsed, the value of x becomes bigger than or equal to 2, and this transition is allowed to be taken only after this. Okay, let us continue. Let us look at another feature. We want to say that in at most 5 units, the train will enter the crossing. So once x is set to 0, it needs at least 2 time units to enter, but it cannot be in the near state for more than 5 time units. That is modeled by attaching a constraint to the state. So this was a constraint on the transition. This transition can be taken only when x is bigger than or equal to 2. This constraint tells that the system can stay in this state only till the value of x is less than or equal to 5. Let us continue. What about this? Here, once again, we said that between approach and lower, there is exactly 1 minute delay. To do that, we add a clock to this system. This is a clock different from here. However, all clocks are assumed to go at the same rate and the same rate of time. Okay, so when initially y would be 0, and as and when time elapses, the value of y also increases. And when this transition happens, that is when the approach signal comes, then the value of this clock y is set to 0. And then from 0, the value of y keeps increasing along with time, and this transition can be taken only when the value of y is exactly equal to 1. Okay? Similarly, between exit and raise, there is exactly one time unit. Now you can reuse the same clock. We do not have to. Firstly, let me tell you that you can add multiple clocks. For example, I could have said, say, y1 is set to 0, and then y1 equal to 1 will be the constraint for this transition, but that is not needed because we can reuse the same clock. So in this transition, y is set to 0, and in this transition, y is asked if its value is 1. Now after this, we are not worried about the time at which the train approached. So we can reuse the same clock. We can say that when this transition is taken, the value of y is reset, and then this transition can be taken only when the value of y equals 1. Okay, let us continue. This is about the gate. We need to make a small change. If you say, it says that the time taken for the gate to come down, the execution time is at most 1 minute. So how do we model it? We say that the gate is up. When it receives the signal to lower, it goes to this coming down state, and here are the timing constraints. When it receives the signal to lower, it will reset a clock Z to 0. So this is the clock of this system, and it can stay in the coming down state for up to 1 time unit. Okay, and again, once the time is 1, it has to take this transition and it will go to down. Now from the down state, in the down state it can stay as long as it wants. When it listens to the raise signal, it will reset a clock Z and it will go to the coming up state. Now it is coming up, and how long can it stay here? It can stay for at most 1 time unit, and when the time becomes 1, then it has to go here. Okay, so this is a way in which we can add timing constraints into the model. What are the basic mechanisms that we have seen? We have what are called clocks. Clocks are real valued variables. They are part of the model, and then as and when time increases, the values of the clocks increase at the same rate. And how can we use the clocks? We can reset the clocks during transitions. That is this reset operation. We can use constraints on clocks in states. This will say that the system can stay in this state as long as the value of x is less than or equal to 5. And on transitions, we can have guards. This says that this transition can be taken only when the value of y equals 1. Okay? And now you can use the usual composition operator for these timed program graphs. In some sense, these are program graphs with timing constraints. And the synchronous product will give the timed transition system for the joint behavior. By synchronous, what we mean is initially the system is in far 0 up. When there is an approach, far goes to near and 0 goes to 1, and then both the clocks are reset. Because of the invariance present in the state, we need to be a bit more careful when we define the synchronous product. But let us not worry about it for now. As long as you understand that there is a way in which we can add timing constraints by making use of clocks, we can proceed to the next part. So here is a summary. Timed transition systems are transition systems with clocks, with a finite number of clocks. And clocks can be used in the following ways. They can be reset in transitions to start measuring the time, and there can be guards on transitions to impose timing constraints on actions. And guards can be used, constraints can be used on states to limit the time spent in a state. Like new assembly which corresponds to transition systems, there is a model checker for timed transition systems. It's called Upal. You can go to this website upal.com. It's a commercial software. However, for academic use, they have a free version. So you can try to download this version and check it out. We will now see a demo of the example that we saw in Upal. But before that, let me mention that the founders of Upal, Kim Larsen, Paul Peterson, and Wang Yi, were awarded the Computer Aided Verification Award for the tool Upal. So Computer Aided Verification is a popular conference dealing with formal verification. Let us now see a demo of Upal. So this is how the Upal model checker looks like when you open it. When you download the software from the web page that I have mentioned, it will have installation instructions. And when you open it, this is the screen that you will see. So this is a graphical user interface. You can make transition systems by making use of this GUI. Let us first start making this train transition system. So this is the transition system that we want to make. It has 3 states, and these are the actions and resets, invariants, and guards. So each transition system is called a template. Let's call this template as train. Now, this is the initial state. When they have a double circle, it means it's the initial state. There are 3 states here. For adding states, they have a button here. You just click on it and do this. 3 states have been added. Now what we will do, we will edit these states by giving them names. So whenever you want to do that, you have to click this button. Now let us edit location. We will give the name far. It's initial. There are no invariants. For now, don't worry about what urgent or committed is. Let's press OK. So there you go. Here you have got a name for this state. Now let's do the same thing here. Edit location. Call this location near, and the invariant is x less than or equal to 5. Now there is an option to check syntax. Go to tools and check syntax. It shows something in red. It says unknown. When you bring it close, it says unknown identifier. Yes, indeed, we need to declare a clock called X. Either you can declare it along with the train, or you can place a global declaration. In this case, we could have declared it with the train because X is not used anywhere else. Okay. However, you could as well declare it in a global fashion. Doesn't make a difference for this example. Let's continue. Let's add transitions. For adding transitions, this is the button you need to press. Let's first make the diagram. Okay. We have not yet given names to this. So this will be in, and the invariant will be x less than or equal to 5 here. You can also move the names wherever you want for clarity. Now let's add the following information to this edge. You do edit edge, forget what this select is. There is no guard, but there is a reset, and this reset is called an update. What you do is you update the clock x to 0. Now there is something called a sync. This says, is there a synchronizing action? If you see, the train sends a signal approach and the controller has to listen to this signal. So the train is sending this signal. So we will, in Upal, whenever it's a signal which is being sent, you have to add this exclamation and declare what is called a channel approach. So this channel means that it's a means of communication between different transition systems. And the train and controller communicate via approach, which is one of the channels. The train sends the approach signal and the controller listens to it. When we do the transition system of the controller, it will become clearer. Let's finish off the train. What about this edge? It has a guard x bigger than or equal to 2. Now, what about this enter? Note that this is not a synchronizing action. Enter is present only in train. It's not present anywhere else. So we do not have to give any synchronization. And there is no update as well. Let's leave these things blank. There is no update and there is no synchronizing channel in this transition. Okay. So this is the guard. And what about this transition? Here there are no guards or updates, but there is an exit signal, and this is a synchronizing signal because the train sends this signal and the controller has to listen to it. So we need to give exit, and this is the sending. So we need to declare a channel called exit as well. Okay. Now we want to add another transition system. So you say go to edit and say insert template, and there you can change the name of the template to controller, and controller has 4 states. So this is the initial one. Click on this to add states. Let's give names 0, 1, 2, 3. There are no invariants. You can just delete this. So Upal does not allow you to call it just 0. So just write it like this. It's the initial. There is no invariant. This is 1, 2, and 3. Now let us add transitions. Note that controller has a clock Y. So we can make a local declaration here saying that clock Y. For the train also, let us change the global declaration to a local declaration saying clock X. Okay. Now let's add information on the transitions. On this transition, there is an approach. So here, let's finish off the update. Y is set to 0. And what about the sync? It listens to the approach signal. So here we have to say approach followed by a question mark. This is how Upal talks about listening signals. Okay. And what about this? Here the guard is y equal to 1 and the synchronizing. So here it sends the signal lower. Okay. And we need to add a channel lower. Okay, this is a global declaration because it's between transition systems. Now what about this one? Here it listens to exit and does an update of y to 0. And finally here there is a guard y equal to 1 and it sends the signal raise. Let's add the declaration raise. Okay, let's check syntax. So nothing read here, nothing read here. Now there is something called system declarations. You need to define the processes that are part of your system. So there is one which is train, call it process 1, or maybe let's call process train. Then process controller is the template controller, and the system is made of process train and process controller. For now, we also need to add the gate. So what we'll do, we will insert template and call it gate. How many states there are? 1, 2, 3, 4. So up, coming down, down, coming up. So this is up, coming down, and the invariant was z less than or equal to 1. So this means we need to add a clock z to the gate. And now this is up, there is no invariant. Sorry, this is down and there is no invariant. And now the invariant is, okay, the state is coming up and the invariant is z less than or equal to 1 yet again. Let's now add the edges. So this edge updates z to 0 and listens to the signal lower from the controller. You can even redesign your state diagram. Now this is lower and z equal to 0. Okay. Edit edge, update is z equal to 0 and the synchronization is it listens to the lower from the gate. And here there is no action and here it is update to z equal to 0 and it listens to raise. Now in the system declarations, we also need to add this process. So the entire system is made of train, controller and the gate. Let's now check syntax. Nothing wrong here, nothing wrong here as well, and nothing wrong here as well. Now what we can do is we have defined the three transition systems. This was our editor. We can now simulate it in the simulator. Yes. So you see, this is how it looks like. Initially, these are the states, and you can also see it in a different way here. So process train is in far, process controller is in 0, process gate is in up, and this will also give you the values of the constraints satisfied by the clocks. There are 3 clocks here, X, Y, Z, and this will tell you the constraints satisfied by the clocks. Initially, all of them are bigger than or equal to 0. And all of them are equal to each other because nothing has changed and they are just evolving with time. Then you can do next. So the train has sent the approach signal. So the train has sent the approach signal to the controller. So the train has gone to near and the controller has gone to 1 and the gate is still up. You can keep doing this. Now the train is in and you see that something is going wrong. So the train is in, the controller is still in this state and the gate is still up. So this means that we are allowing for the controller to stay in this state as long as we want. So we should have added an invariant to this controller and in this state. Let's add it and see what happens. You can stay here only as long as y is less than or equal to 1 and then you need to take the transition. Similarly here, we need to add the invariant y less than or equal to 1. Okay, let's now do the simulation. So initially far 0 up, then the train sends the signal approach to the controller, controller goes to 1 and now the controller sends the lower signal because the time is now 1 and the train is still near. Here the controller sends the lower and the gate is coming down now. The gate is down and now the train comes in. Okay, let's continue. The train has exit. So when this sends the exit signal, the controller goes from 2 to 3 and now what happens? The controller asks the train to raise, the controller asks the gate to raise itself. So it sends raise and goes back to 0. Right now the gate is coming up and now it is up. So we are back to far 0 up. So you can do many more simulations. Here there were just 3 processes. You can have multiple trains and then you can see what happens. So for defining multiple trains, there are parameters. You can take a look at the Upal reference manual to see how you can do it. Well, this was the simulator. We can also do verification. Verification can be done using some kind of CTL properties. What do we want? Let's say in every path, okay, let me write the property that I want to check. In every path, it is not the case that the train is in, but the gate is up. Essentially, nowhere it should be true. I mean, nowhere it is true that train is in but gate is up. So in CTL, this will be written as AG, not the case that train dot in and, so here you have to use two ands in Upal, and gate dot up. In Upal, G is denoted as open bracket, close bracket. Okay. So A, open bracket, close bracket. It's not the case train dot in and gate dot up. So this is the query that we want to check. Let's check it. So here is the error. It says that train is not a structure. Well, the mistake that I made was this should be process train, process gate, because these were the processes. Let us now check, and it says that the property is satisfied. So it is never the case that you will reach a state where the train is in and the gate is up. So we saw a demo of Upal. We saw how to add states, transitions and clocks. We modeled the train gate controller example. We had a look at its simulation environment. This graphical user interface is very helpful. And then we saw how we can check certain properties. For more information about what kinds of properties you can check and what else can you do with the states and transitions, you can have a look at the manual which comes along with Upal. So in this unit was meant to give you an introduction to Upal. So let us now see one more example of a timed transition system. Here is a circuit. This is a NOT gate, this is an AND gate, and this is a NAND gate. You are familiar with this. Suppose I also give you some intervals along with this circuit. Let's see what it means. Usually when the signal is 0 here, immediately the signal becomes 1. When the signal is 1 here, immediately the signal becomes 0. Similarly, if x and y are 1, immediately P2 becomes 1 and so on. So the change to the output is immediate. You assume that there is 0 delay in the change. However, there could be some non-negative time between the change to the input and the change to the output. So this is called inertial delay. This says that when the signal changes, the NOT gate needs at least one time unit to change its output. Moreover, within 3 time units, it will change. For example, it says that suppose this is 0 and this is 1. Suppose x becomes 1. Then P1 does not become 0 immediately. The system is like this, 1, 1 for at least one time unit. And between 1 and 3 time units gap, the output changes. That is what this inertial delay means. Let me explain it with a picture. So suppose this is the NOT gate. Assume that this is the timeline. Assume that this is how the input x changes. 0, 1, 1, 0, 1 and so on. So here it is 0 and P1 is 1. So up to this it's fine. However, the value of x changes to 1. So in a normal circuit, immediately this should have become 0. However, let's look at the time for which x is 1. So the signal is 1 for less than one time unit. And this is the bound on the NOT gate. So P1 does not change at all. And now x becomes 0 again. So P1 is still 1. Now you see x becomes 1. And it's staying at 1 for more than one time unit. So within 3 time units, P1 should change. So P1 becomes 0. As X becomes 1, P1 becomes 0. And now it stays here. Yet again, X changes and the signal persists for at least 1 time unit. And within 3 time units, P1 becomes 1 and so on. Okay, I hope you understand what inertial delay is. So some notation, we say that the gate is stable if the outputs and inputs match the truth table. For example, 1, 0, 0, 1. It's said to be unstable if the input outputs do not match the truth table. So here in this portion, the output is stable. The system is stable. Here, the system is unstable. The gate is unstable. Here, the gate is stable. Here, the gate is unstable because both input and output are 1. Here, it is stable because input is 1 and output is 0. In this part, it is unstable since both input and output are 0. Here, it is stable, and so on. So this inertial delay just says that when the input to a gate changes, the gate will be unstable for at least 1 time unit, and within 3 time units, it has to become stable. That is what it means. Okay? Let us now model the circuit using timed transition systems. What we will do is we will give a timed transition system for each of these gates, and the synchronous product will give us the timed transition system for the entire circuit. So let's start with the NOT gate. It has a timing delay 1, 3. Now, how do we give the state of this NOT gate? The state is given by the value of the input, the current value of the input, and the current value of the output. So X, P1. And there are 4 possibilities. The red ones are the unstable states. The green ones are the stable states. Assume that initially the gate starts with X equal to 0 and a stable state. Suppose X becomes 1. So this is the signal that X is becoming 1. The value of X should change to 1 and it should stay in this unstable state for at least 1 time unit. And how do we take care of this? We set a clock Z1 to 0 during this transition, and we allow this transition to be taken only when the value of Z1 is bigger than or equal to 1 and at most 3. And what is this transition? This transition is setting P1 to 0. So this is the signal. So you can look at it as an alphabet. You can look at it as a letter actually. Okay. Just for clarity, I have written it as X:1, but you can think of it as an action, name of an action like approach, enter, exit, and so on. Okay. So when X became 1, the value of Z1 was set to 0, and P1 can become 0 only when Z1 is bigger than or equal to 3 and it has to be less than or equal to 3. Okay. However, when the system is unstable here, it might so happen that the value of X changes back to 0. In that case, the system can go back to its stable state. Look at this. It says that the system can stay unstable for at most 3 time units. Note that the circuit is not forced to become stable within this time unit. What we say is that it will become, for it to become stable, it needs at least 1 time unit, but it may choose not to become stable within this time gap and go back here. However, if the time becomes equal to 3, then it has to go to either one of these 2 states. So there is an invariant Z1 less than or equal to 3 in this state. Let me explain it with the symmetric thing here and we will understand. Now suppose X is 1 and Y is 0. This is a stable state. When X becomes 0, the circuit goes to this state. This is unstable. X is 0 and P1 is 0. Now there are two choices. Either the circuit becomes stable because the value of P1 changes, and for this to happen, the value of Z1 should be between 1 and 3, or the circuit becomes stable because the value of the input changes before it becomes stable. Okay? And that is modeled by saying that there is a transition here which makes X to 1. So this is the alphabet, this is the action marking X to 1, and this should happen within 3 time units. So within 3 time units, either P1 becomes 1 or the input changes. For this to happen, for the system to become stable, you need at least 1 time unit. So you can assume that there are invariants Z1 less than or equal to 3 on both these states. So this is the timed automaton model of this simple gate. You can see that there is some notion of non-determinism coming because of time. Okay, the system can choose to go to the state non-deterministically within 1 to 3 time units. Also, there is non-determinism due to action. At some time between 1 and 3, it can either choose to do this or choose to do this. Okay, so this is the timed transition system model of this circuit, rather this gate. Now you can also do the same thing for this gate. For this gate, you have 2 inputs and 1 output. So a state is given by value of x, y and p2. So there are 8 states. However, one of the states was not reachable, so we have not written that. So see, 0, 0, 0 matches the truth table. So this is stable. However, 1, 1, 0 does not match the truth table, which is unstable. You can go through the transitions and see that they match the inertial delay of 1, 3 for this gate. So it says that, for example, when the gate is at 0, 1, 0, and if the value of x becomes 1, then the gate is unstable now. It can become stable in multiple ways. Either the value of the inputs can change or the output changes. For the output to change, there is a constraint. Okay, and you can assume that there are invariants on every unstable state. You can be unstable for at most 3 time units. So there is a bounded inertial delay. Similarly, for the NAND gate, you can draw a similar timed transition system. Now, the synchronous product of these 3 timed transition systems will give us the timed transition system for the entire circuit. And the synchronization is happening through these actions. For example, this one says that x is becoming 1, and here there will be synchronizations on if x becomes 1, what to do, and so on. So if you want to model this in Upal, you might need to have another automaton which keeps sending the signals x becoming 1, x becoming 0, and these will all be receiving the signals that x has become 1 and y has become 1. So the synchronization is over these actions, and Upal also allows you to do the synchronization over multiple transition systems. For example, if you have another transition system which is sending the signal x colon 1 question mark, these 3 can, x colon 1 exclamation mark, these 3 can use x colon 1 question mark. So they all can listen to the synchronization. What you need to know is that this is just the handshake operator, which we had seen in the first unit. On a state, when you see this action, all the transition systems that can play this action will take the next step. That is what it means. Okay, that is what synchronous product means. So let me summarize. In this unit, we have seen how to model timing constraints in systems. And for doing that, we have given this definition of time transition systems. We have given you an idea of what time transition systems are and how you can model it and verify certain properties using Upal. So you can, so this unit gave you a glimpse. If you want to know more about time transition systems, this is the seminal paper which introduced the notion of timed automata. So when we wanted to model check usual transition systems, we made use of results from Bucci automata and finite automata. For timed transition systems, there is something called timed automata, and all model checking results are based on the results on timed automata. For more information about timed transition systems and Upal, you can find a lot of online references. You could also take a look at the book Principles of Model Checking, which we had prescribed. There is an entire lesson on timed transition systems.